describe and follow some very distinct phases or stages of population growth. Cells are growing top and bottom. The population size, cell number, increases in predictable and characteristic fashion for each gene species. In other words, each of these phases that we're going to talk about will have characteristic appearance for each different organism. And it will have a different appearance for the same organism under different conditions. Different environment. Okay? This is what we call a bacterial growth curve. Bacterial growth curve. I'm certain you've seen bacterial growth curves, you've seen population growth. Probably haven't seen a human population growth curve, but you've probably seen population growth curves that fall or rise and so forth. Now this is the old terminology. This is what your book presents, but this is rather old and dated. Old bacterial growth curve. Here we see four distinct phases. The lag phase, the exponential phase, sometimes called the log phase. I'll try to avoid the term log because lag and log you can get mixed up with. The stationary phase and the death phase. Now, in the last 10 years, I don't know why it's taken so long to filter down to some textbooks, but we've come to realize that there's really another phase there at the end. And really, this decline, this death phase, doesn't go all the way to the end. It doesn't go all the way down to the x-axis. But rather what happens is it tails off into what's called the phase of prolonged decline. That phase of prolonged decline can be measured in years with some types of that period. Years. So now we talk about the lag phase. We talk about the exponential or the log phase. This is sometimes also referred to as the geometric phase because of the geometric fashion in which these organisms multiply. Stationary, decline, the death, and the phase of prolonged decline. By the way, death is sometimes called the decline phase. But you see that I try to be consistent in my terminology when I write quizzes and when I write questions. But if you see it in the literature, it's the decline phase, that's the death phase. So let's talk about these. Talk about the lag phase. Somebody, you hear the word lag, what comes to mind? Slow, yeah. Slow, lethargic, not a lot going on. And nothing could be further from the truth in the lag phase of a population growth curve. The only thing that's not going on is binary fusion. Notice that this line is horizontal. There is no increase in numbers. And I also want to point out to you that this is a logarithmic scale. Your book makes a very good example of why we need to use log scales when we talk about bacterial numbers. This is a linear scale. This is a logarithmic scale. Now, this is 100, 10,000, a million. What is that? 10 billion. So when we plot these numbers, we're plotting them on what we call a semi-log basis. Semi-log plot. Some of it is arithmetic, the other half is logarithmic. Okay, well, the lag phase. The number of cells does not increase, but there is intense physiological and metabolic activity. Intense. In many cases, depending upon the circumstances of this lag phase, let's put on here over here. It may be very, very short, or it may be quite prolonged, maybe a day or so. Because what the cell is doing is it's adapting itself to the new culture conditions. It's adapting itself to the new culture conditions. So over here now, I talked about, let's take that flask of medium that I showed you. Let's assume it's tryptic soy broth. That's the same medium that I showed you with cultures that are broth cultures. We're going to take E. coli out. put it into a medium that's called nutrient broth. I think nutrient broth is spelled out for you there in the handout, but it's nutrient broth. Now this is a lower concentration of nutrients than what we find in turkey soy broth. So when we now take these microorganisms that they've grown in this richer medium, and we're going to transfer them to a less rich medium, this is what we call a step down culture. And it will take a considerably longer period of time during lag. The cells spend more time in lag in order to prepare themselves to grow in this relatively weak medium. A step down culture. On the other hand, we take cells out of typic soy broth, and we can put them into a medium called grain-hardened fusion. One of your colleagues wanted me to spell it. Grain-hardened fusion, DHR. Very rich medium. Very expensive. Very expensive. Not the things that will not grow on a KSA or typic soy will grow on there. But this is what we would call a step-up culture. The organism is going to spend very little time in lag phase because everything has been provided to it. Now, it may need to make some transport enzymes, transporters, may need to make some ribosomes, depending on how old that culture is. But normally, it's not going to take very much time at all. Now, if I have a culture of typic soy broth, and I transfer it to a new culture of typic soy broth, what can you tell me about the lag time there? No, let's suppose we're just getting started. You see, there would be no lag phase. But if it had used up all the nutrients in the original typic soy broth culture, now it would be transferred into the same medium. It's in the same medium, but it still has to replenish enzymes. It has to replenish ribosomes. Okay? All right. Cell is a priest. The cells are preparing for growth. They're preparing for growth. In this new cultural environment, they're preparing for growth. They're going to be making, like, for example, it's been shown that the amount of RNA, paper RNA, messenger RNA, is eightfold during lag phase. The number of ribosomes increases. The amount of ATP increases. So it's metabolically very active, it's just not surviving. Producing key metabolism. The other day, I mentioned the term fueling metabolism. Fueling, F-U-E-L-I-N-G, fueling metabolism. These are compounds that the cell needs in order to grow. They can use stuff for making them. And we talked about step up, step down, shift up, shift down. There's the secondary symptom. Okay? Now, if you look at this, well, let's go to this. There's our lag phase, there's our log phase. Now, notice it doesn't immediately go into the log phase. It doesn't immediately go into that. There's a phase right in here that we don't talk about. You find it typically only in more advanced physiology textbooks. But this is where we're seeing a shift in that cell population where some of the cells are starting to divide. Over here, I've drawn on the board a bell-shaped curve. In that population of lag phase cells, they're not all at the same point metabolically. The number of cells along the x-axis. This is what I call ready to go. Ready to undergo binary fission. And then as it goes up, more cells. We're going to have some cells that are at this age. They're not yet ready. They truly are lagging behind the population. And we've got some over here that are ready to go. And clearly this number that are ready to go would increase as time goes on. Most of these cells are at some stage of preparation. But it will take a period of time for all of these cells to go from this step to this step. That's what we see right here. But once they do get all over there and ready to go, then we are in exponential phase. Log phase, geometric phase. Again, your book slope of that curve is very characteristic for a given organism, in a particular medium or a particular set of circumstances, environmental circumstances. The growth rate. This can be influenced by several factors. We talked about some of them. Temperature. We can mathematically express that line right there. That growth rate can be